Également.
T'es insulté?
Non. Est-ce que tu as parlé du Brésil? Moi j'ai lancé mon...
So we now resume. Thank you. The next topic is IPv4 versus IPv6. A topic that, as you can imagine, is creating some confusion and problems. Let's start with the easy things. You have done in lab 3, if I remember well, a programming exercise where you had sometimes to use IPv4, sometimes to use IPv6. That's the first thing that we need to remember. When you write an application program, then it's up to the application program to select IPv4 or IPv6. And in practice, it is like selecting two different networking stacks, one for IPv4 and one for IPv6, that are treated by completely different sockets in the operating system. Important to remember is that, therefore, the application program is IPv6 or IPv4 dependent. If you take an application program written for IPv4, like for example the code on a printer, and you want to go with IPv6 into it, it won't work. However, the protocol itself, the protocol you use to go to the printer or to go to a web server, is independent of IPv4 or IPv6. So there is not an HTTP v6 or an HTTP v4. It's the same protocol. The TCP itself is the same. It's just how TCP uses IP that the choice is different. But it's visible to the application code. Therefore, the program needs to be made aware. In the lab, we went to a web server called lca.epfl.ch that exists in both IPv4 or IPv6. If I have what we call a dual stack host, a machine that has both IPv4 and IPv6, not just in software. I mean, any software you buy today, any iPhone, any PC, any Macintosh has both IPv4 and IPv6, but it's not necessarily sitting on a network where both works. We know, for example, the EPFL wireless network doesn't support IPv6, so if you use wireless, you're not a dual stack host on the EPFL network. You need to go to the INF 019 room to get IPv6 support. Assume Lisa is on both IPv4 and IPv6, has both the network and the software to run both, and then sees something like lca.epfl.ch or newstuff.epfl.cn or infoscience.epfl.ch. Which of the two will Lisa use to go to those servers? IPv4 or IPv6? What do you think? There's no clicker for that because it's a too intellectual question. So I'll solicitate answers. Who has an idea? Yes? Thank you.
IPv4 because it's more commonly used?
IPv4 because it's more common use, so you're a conservative person, right? You prefer to use the old stuff because it's proven. That's a valid answer. However, if you have IPv6 and IPv4, you might think the other way. You might say IPv6 is the new stuff. Therefore, I would prefer the new stuff. Well, in fact, the rules are exactly the ones I said. If both servers support IPv4 and IPv6, that is the case for that one, in principle, you will use IPv6 by the dogma that what is new is better, which is generally true for software, except if it's very new. But if it's, now, of course, if you want to go to IPv6, if the machine does only IPv6, if you have no choice, you will use only IPv6. That's very rare today. There's practically no system that is IPv6 only, but it will come in the future. Very soon, there will be lots of places that have only IP, well, I say very soon, every year, but sometime in the future, there will be places that have only IPv6. But certainly, there are places like InfoScience at EPFL works only with IPv4. If you have an IPv6 only machine, you're in trouble. Well, the first thing to realize is the trouble is a real trouble. V4 to V6 is not possible. If you have a V6 only machine trying to access a V4 only machine, you cannot send IPv6 packet that by some magic would find their way to the machine. We will see how we can make things that are not magical to make that happen, but if you do nothing, that won't work. Now we've seen what is done when we know what the two ends are doing. But how do we know what the other end is doing? I see a website name that I got from a page, newstuff.cn, .epfl. So that's the EPFL branch of that's the branch of EPFL in Shanghai. Then, how does the local machine here know whether that remote machine has IPv4 or IPv6? What's your best guess? Let's see the answer. Then the correct answer is, of course, none of the above. I mean, 1 and 2 are a bit cumbersome. You could send a ping and try, but it's not the general philosophy. How do we know something about the server? Well, the correct answer is via DNS. So DNS plays a central role in the IPv4, IPv6 story. We've seen that in a DNS server, there are records that give what is the IPv4 address of that name and the IPv6 address of that name. So it's very easy for your machine to ask if your machine does both V4 and V6. Well, let me ask the DNS server, what are both addresses, if they exist, of that other guy? So typically, a dual stack machine will ask for both IPv6 and IPv4 record. And if you get both answers, you infer that both are possible. So we use DNS with the belief that if authoritative servers, if they put IPv6 records for those names, it means they have IPv6 connectivity to those names. Of course, if they don't do it, things won't work. That's and as we've seen, nobody authenticates and verifies what is put in DNS. So if EPFL DNS servers put an IPv6 address for machines that have no IPv6 connectivity, then people will try to connect with IPv6 and see it doesn't work. If the software, like Macintosh, is smart enough, it will try with IPv6 a number of times. It will see it doesn't work. Then it will try with IPv4. So this is DNS that will solve the issue. By the way, how do we access DNS? If I am on this machine, I have both IPv4 and IPv6. I have now two ways to access the DNS server, either IPv4 or IPv6. Both are possible, both can be used, and both can be used to provide answers to both types of mapping. For example, it's perfectly possible to configure your machine to access the DNS server with IPv4 only and get answers over IPv6. Although many implementations will tend to use mimicry, say if I ask an IPv6 question, I will go to an IPv6 address of the DNS server. But there are lots of cases where this would not be good, particularly this case here, where this machine has both, doesn't know what the rest of the world is doing, so it would be stupid to send an IPv4 query using IPv4 for an A record, and when you ask for a quadruple A record, use it over IPv6. You can send it in one UDP message, so that is what is done typically. So the first thing to remember, and the first element of complexity, is that DNS contains mappings about addresses, but the reachability of DNS is a different story. DNS servers can be reached over IPv4 or IPv6 or both, and they contain answers about IPv4 and IPv6 in both cases. By default, many machines use an IPv6 DNS server under Windows, but everything is possible. Voilà. What we've seen so far is how we detect whether we choose IPv4 or IPv6. Now let's dive into the heart of the main problem, which is what do we do when we are in a heterogeneous situation where part is IPv4 and part is IPv6. I repeat that we've seen it zillions of times. IPv4 and IPv6 are incompatible. That's a design choice of the IETF, of which we bear the consequences now, which means that there's a number of things to solve, essentially. All the possible combinations of things that are IPv4 or IPv6 and not both, and things don't work. To better understand what can be done and how to solve it, it is useful to make the distinction between those two words, interworking and like-to-like access, sometimes called simply tunnels. Interworking is the real hard problem, the one we would love to solve in all cases. I have an IPv4 only machine. I go to a web server in a part of the world where there's no IPv4 addresses, so that server has an IPv6 address only. How do I talk to that server? In principle, it's impossible, but it's completely unacceptable that it's impossible, right? You still want to get that, so we need to find a solution for that. That's the interworking. Another milder version of the problem is called like-to-like access. Like-to-like means I have an IPv6 machine here, and I want to do an upload, for example, of a funding request to a government agency. Many government agencies, they do things like, now you have to do it with IPv6. Right? So some American government agencies do that. When you submit your Word file with the application for a few $1 million to do a few papers with PhD students, it has to be submitted with IPv6. So you have a machine in your lab that does IPv6, but you do it from home at night because you're late, and then at home you have only IPv4. How do you solve that problem? This is called like-to-like, in the sense we go IPv6 to IPv6, but the network in between is not entirely IPv6, so there is not connectivity at the network layer. And vice versa. You could imagine also having a 4-to-4 problem over an IPv6 infrastructure, which might happen in the future when you've moved entirely to IPv6 everything, and you still have somewhere a lift or a printer or a doorknob or a sensor that has only an IPv4 address. How do you talk to that machine? In this hour, now we will study only the beginning of this problem, and next week we will talk about the other problem. Well, there is a very easy solution. Easy, but against the principle of the internet. It's called the application layer gateway. Assume I have someone with an IPv6 only machine. That's Homer. He was unable to configure it with IPv4 and wants to go to a web server, for example, infoscience.epfl.ch, that works only with IPv4. How can you do it? Well, if you find somewhere a web proxy that has both, then problem solved. So that is a very convenient solution because web caches or DMZs tend to exist in many companies. So if you have a company that deploys IPv6 only, then it is fairly easy to do that. Of course, the application layer gateway must be able to speak both IPv6 and IPv4. But the good thing about it is, other than installing both IPv6 and IPv4, it is the same application layer gateway as we did before. So there is no special interworking, in fact, because everything at the level of TCP and above is the same. So that's the good news of the layering approach. That solves the problem easily. There might still be a number of side issues, though, like this one. we assume the final machine is www.epfl.ch, right? Then this machine, which is this one here, works only on IPv4. Because most of the time, I mean, it's hard enough to have a server that works and does the job and doesn't crash and is up to date. If in addition, you need to always make sure it's both for IPv6 and IPv4. So in practice, very few people take IPv6 seriously unless they're forced to. So you work in an industrial environment or a given wireless network operator, for example, that has only IPv6 addresses, then you start taking it seriously. Otherwise, if you have IPv4, you don't take it seriously. So the way it's done at EPFL is we have an application layer gateway that is not in a firewall somewhere in the company, but it's just another web server that pretends to be www.epfl.ch and has an IPv6 address. The last time I sampled the system, it was www.6.epfl.ch. And if you do Wireshark to see what happens, in fact, it is just simply relaying your request. So when Homer, in that case, would go to www.epfl.ch, the request will go here, not because Homer's PC is configured with a proxy, which is one way to achieve this, but through some other mechanisms, it will automatically go there. And then this machine, which is a hidden proxy, will simply repeat the request, forward it to the true IPv4 server that will then do the job like we've seen before. The question is how will Homer know? How will the PC know that it has to go to this application layer gateway? You're somewhere at EPFL, you type www.epfl.ch, you can do that test. If you have IPv6 connectivity, you disable IPv4, it will work. But how does it know it has to go here rather than there? Any volunteer? Yes?
I think the logic has to be coded into the application. So they do an DNS lookup for the name, and if it's only IPv4, then you have to set a proxy for the system.
So the logic has to be coded in the application? That's true and not true. It's true, but the logic is in principle always coded in any application that accesses something via a name. Will first, if you use sockets, in the lab, you're completely unable with sockets to give a name, right? You need to give a destination host that has an IP address, and you need to decide whether it's an IPv4 socket that you open or an IPv6. So any application logic, except for the very specific applications that don't use names, has to go through DNS. So this will typically be how this is done. So the very obvious and sorry, whoops. This is 46. The answer is again DNS manipulation. So at EPFL, you're in your company, you have the true stuff on IPv4. You want to say to the government that you support IPv6. So what will you do? You will make an application layer gateway, and in the DNS, you will write different answers for the A and the quadruple A records. So if somebody asks, what's the IP address of www.epfl.ch? If the question is, what's the IPv4 address, you will get this one. If the question is, what's the IPv6 address, you will get this one. So we use DNS here, and that will work, of course, at the penalty, performance penalty. This guy will be a relay in the middle. Now, if BART is using IPv4, in this specific case, as a result, the PC of BART will directly go to the final server, and the application layer gateway will not be used. Right? What will happen now if Lisa, and if Homer had IPv6 only, it went through the application layer gateway. BART had IPv4 only, it didn't go. Now Lisa has both. She's smarter usually. So what will happen to her? So let's see your solutions. You didn't see the error message I got? Okay. I am betrayed by the... It's impossible. It's impossible. It's like, I mean, 1 or 2 years ago, there was electronic voting in Belgium, and some candidates had always exactly 1,024 or 2,048 votes. So always powers of 2. So it's like this one. Don't believe it. Well, let's try. Let's be bold. Let's try again. But I'm not sure it works, right? Yes. Oh, now we got. So I got 50 answers. So the majority says no, which is very brave, but in fact it's going to be yes, which is paradoxical. But if you, I mean, it's yes or no, it depends. It depends what Apple and Windows do, and it changes at every patch of the operating system. But very often what operating systems do is if you speak IPv6 and the destination speaks IPv6 and IPv4, you prefer IPv6. Okay. So if Lisa's PC, which I tested on my PC and does it, then we will speak IPv6. Therefore, when we will go to the final thing, in fact, we will go to DNS, and there is no way for this guy, or there would be ways if it would be coded a bit smarter, to find that the IPv4 is different from the IPv6 address, but you don't know whether they are different because IPv4 is an application layer gateway that is put for the poor guys who have IPv4 only, or it's the other way around. Everything is IPv4 in fact, but IPv6 is here for the high-tech guys who use IPv6. So we don't know, in fact. So if we take the modern approach, which consists in saying we believe IPv6 is going to be deployed more and more, the side effect is that we will go through IPv6, which means that there will be a performance penalty. You will see it in the delay. If you instrument your delays, it takes longer if you enable IPv6 than if you disable it on this machine, which is, of course, a paradoxical treatment. But this is what will happen to poor Lisa here. Voilà, we have seen our first, yes?
Can we put a flag from the answer, in the answer from the DNS server to Lisa's PC, saying that this is a gateway, not the...
Yes, we could put something like a preference field, like in BGP or something in the DNS to say, I have both, but one of them should be preferred. Yes. Perhaps that will come. Perhaps you should propose that to IETF to put this preference. That's a good idea. What are the pros and cons of this? Yes?
I don't understand why they or someone decided that IPv6 should be preferred if both are available, because as we saw, DPFL, it introduces overhead, and only actually if you don't reach a destination because they have no IPv4 address, then IPv6 makes sense to be used. So why do we have the preference by IPv6 if it creates mostly overhead and is not only useful actually if you can reach it otherwise? Why do we do that?
Yes, so perhaps this case is not the typical case. That might be part of the answer, right? So it's true that if you're in an environment where most of the things are, well, the true thing is IPv4, and we add IPv6 for decoration, then this is not a good idea. But the belief in IETF is that IPv6 is not decoration. If you introduce IPv6, you move to IPv6. Right? Now, of course, the reality might be a bit different. So those rules might also change if it's a if this pattern is very frequent. That's an incentive for operating systems to change the rules and say, by default, I would prefer I would like to prefer. Or we have your addition to DNS, that would help. But so far, in many cases, it's likely to be like this. Why is it this rule? The belief is that once you start deploying IPv6, you quickly move to it. Right. At EPFL we don't, but at EPFL we're very special. At EPFL we do IPv6 for decoration, right? So we invest, I mean the EPFL money is, some EPFL money is spent on making an IPv6 network which operationally has no value. I mean, if we would be a bank, we would not do that, right? The network works without IPv6. So since it works without IPv6, we would have it work without IPv6. Or if you decide to move to IPv6, then you make it IPv6 only. And then you put a few transition mechanisms in a corner for the guys who have not yet used IPv6. Perhaps that's, I mean, I'm just conjecturing like you, perhaps that's the reason why this preference is given. We believe if we introduce IPv6, we take it seriously, and then the servers will the most frequent case is the true thing is on IPv6. And an application layer gateway is here only for the few cases that are not IPv6. This is our first mechanism for the interworking with the two. Application layer gateway 4.6, acronym ALG 4.6. Well, it has pros and cons. Obviously pros, otherwise it would not exist. The major advantage is it's transparent to practically everything once you manipulate the DNS correctly, and at the cost of hardware. Well, hardware is very often the brute force solution. If you can throw hardware at a problem and solve it, usually people will do it. It's easier than change the way the organization is working. It has some drawbacks. Well, the hardware, this is store and forward, so you need a lot of equipment that at the end of the day perhaps is not needed. Now it depends, if you're Google and you have huge web servers, then there might be a considerable cost of having, I mean, imagine YouTube having to do store and forward of all the YouTube traffic on 4 to 6 gateways. That's probably not a good idea. Right? You duplicate essentially the size of your server farm by doing that. So depending on the traffic and the use case, it might not be a good idea. The other drawback is, of course, you need, for every application, you need a gateway of that type. So if somebody tomorrow invents a new fantastic application on the internet, then those solutions won't work until the gateways are updated with the new application. Voila, that's all we will see for this part. There's a few additional quiz that I will let you discover offline. Any questions on this? Then if there is not, we move to the next topic. Which is back to the network layer, back to the roots. But now a bit skewed. What we will see is the things that are a bit violations of the network layer, deviations from the network layer. And we'll see 3. Fragmentation, that's the easiest one. And then another solution for interworking IPv4, IPv6. And then the weird things, but very widespread, called proxy arm. So now we forget for a few minutes the interworking issue. We come back to more solid ground. Fragmentation. Fragmentation is due to this annoying fact here that the MTU is not the same everywhere. MTU is the packet size that we have often seen. On Ethernet, 1500 bytes. So that's the useful part of an IP packet that you can put on an Ethernet frame. And we've seen that this number is cast in stone. Now, there are other technologies like technologies that are used, for example, at CERN when they do high physics experiment with massive amount of data. Then we use what is called sometimes jumbograms, so huge packet size, up to 64K or even larger today. But more practically, very often, we see a reduction of the packet size when there are what we call tunnels. We've already mentioned that, but in some cases, we may want to put an IPv6 packet inside an IPv4 packet. And if we're unlucky, this IPv4 packet is itself put in an IPv6 packet. Whenever we do that, we add headers to headers that reduce the practical size. If you put an IP packet in an IP packet, if you put an IP packet in an IPv4 packet, the MTU is reduced by how much? Well, by the size of the header of the inner IPv4, which is 20 bytes. So we reduce by 20 bytes. In practice, as we will see a bit later, when you do tunnels, like VPN tunnels, you do other things. Usually you put an IP packet inside UDP, but also with some authentication and encryption header that might take more than the 20 bytes. So we see tunnel packet sizes that are not all the same. Now, what's the problem when the packet sizes are not the same everywhere in the internet? Well, here is a small illustration. You see one machine sending packets to another machine. So here it is. Then assume that the MTU inside the network is 620 bytes. Those numbers are purely academic. You don't find 620 bytes MTU. I've never seen it anywhere. But they simplify the story. Then this guy is sending a packet to the destination, and the packet is too large. What should the router do in the middle here? What would you do if you would be a router or a router designer? Any volunteer to be a router for 1 minute? Yes?
Well, I would try to reduce my work as much as possible and send back to the source what my maximum packet size is, so I don't get continuously too much package and have to split them up and repackage them.
Okay, so you are like a mathematician. You want to work as little as possible and be smart. So you would say, I don't do this, packet too big, but I send a message back to the destination, packet too big, which will inform the destination of the maximum packet size. That's one way to do. But not everybody is like this. So other routers, and in the original design of IPv4, that's the design for IPv6, by the way. So that's the modern way of thinking. So you're modern. In IPv4, people at that time thought, no, routers are here to transport packets. They should not kill them unless absolutely necessary. So routers fragment. The router will break it into smaller pieces. This is what this router would do. It's an IPv4 router. It will break this IPv4 packet into 3 IPv4 packets, which is a completely weird thing. That's why I put it in my contorted chapter of bizarre things. Musée des horreurs, if you want in French. Right? But it's done in IPv4, and since IPv4 is the dominant thing today, this is what happens a lot. How is fragmentation done? The important thing to remember, it is an IP layer thing, even bizarre, but it's in IP layer. So we're not talking UDP or TCP, it's IP layer stuff. If it's IP layer, that means we are forbidden to look at the TCP or other headers. So this router here, it will break this packet by separating the header, the IP header, from whatever is inside, and will create 3 packets with essentially the same IPv4 header, not exactly, and the data. Now the data was 1400, and now it fits nicely. This is why it took 620. So it will create 3 packets. For terminology, this original thing is called a datagram that fits in 1 packet, and we have one datagram that fits in 3 packets. If we look at what IP header does at this point, the header is essentially the same. The source and destination address are the same. But of course, there has to be something to indicate that we broke the datagram into 3 pieces. Those things are illustrated at the top. Those things are essentially the length and the more fragment flag and the offset. What are those? The length is the length in byte of the packet. We've seen it is present in every IP packet header. So the length indication that's in the IP header is the length of this packet. It is not the length of the original datagram. So this, at 2A, we will have a length of 620. The identification is another bizarre thing that is done by IP. Whenever your operating system generates a new IP packet, it increments the identification number by 1. So all the packets have numbers that are incremented. It's typically done per destination address. The use of this packet number, if you want, is only for fragmentation. So at the source, when the packet was created, it had the number 567. So the 3 fragments will have the same number, 567, written here. This is what will be used to reconstruct the original datagram by having the same number in. And then there is, and that's it, except for the offset. Now what is the offset? The offset is where in the original datagram the packet is. So for the first packet, the offset is 0, which is given here. For the second packet, the offset is 600. And for the, no, why is it? It's only for the second, B. And for the third packet, the offset is 1200. Now, in order to save 3 bits, the offset is coded as multiple of 8 bytes, and it is required that fragmentation always does offsets of multiple of 8 bytes. So you never create a first packet fragments that would be, for example, 599 bytes, but always in words of 64 bits, which was very far looking. If you think about it, that was done in 1979. And already at that time, we thought in bits, in words of 64 bits. Therefore, the true offset that you read with Wireshark in the packet header is in fact the offset divided by 8 to save 3 bits. So this is how it is coded. Now at the destination, we will receive the 3 packets. Here I'm showing them in the reverse order. They arrive perhaps not in the same order. Why would that be possible? Why could there be a misordering?
Different paths. Because
there could be different paths. We try to avoid that as much as possible in the internet, but it's not guaranteed that it won't happen. Then reordering is always done at, reassembly of the original datagram is done always at the destination only. And now, at the destination, we will be able to recreate that. There is still something we need to know. I mean, when I receive, for example, the second fragment, here, if I receive the second and the third, I know where they are in the packet by the offset field. So I can start writing in a buffer at byte 600 what comes in. Now, I still need to know whether the third one is the last or whether there is more to come. There is a bit for that, which is called the more bit or more flag that says there is more to come, and it's put everywhere except in the third. So when I receive those 3, I know where to write them in memory. And in the third one is the indication this is the last. Therefore, I can reconstruct the original packets. Right. Yes?
Why not reconstruct at router 2?
Good question. Why not do the reconstruction here? What do you think? What could be a good reason for that? This is not done. So reassembly is never done by router. you are a high-performance router, right?
I think like if there's reordering or delays, that means that I need to cache and wait until all packages arrives and reassemble them, and I don't want to keep that cache just for someone else's packets.
Correct. So one of the reasons is you're never sure that the 3 fragments will go through this router. If they are here, yes, because there's only 2 routers in this world. But in general, there might be multiple paths. There might be 2 routers connected to this, and traffic might arrive. They are load sharing. So you're never sure that you could get all the fragments. So a router can never be sure. So it's physically impossible.
What if all the routers open the same way, so that the bigger package is fragmented at one side and reconstructed at another?
But even then, right, so let me do another diagram because this one is overloaded. I might have 2 routers connected to the internet, and some of the fragments, like fragment 1, might come this way, and fragment 2 and 3 might come this way. So in that case, none of the routers is able to do it. It's rare, but it can happen. So that's, and in the 70s when that was done, it was considered a frequent case. Now today, routers tend to do what is called per-flow routing. So if you have multiple paths, you try to put all the packets that are the same flow on the same path. So that could be an argument for doing it. But there's another reason. If I'm a router, I don't want to do this, frankly. Sure, I will never want to do this. Why? Well, it's a lot of work, yeah?
I'll have to buffer the packets in my buffer.
Yes, you will need to buffer the packets in the buffer. Plus, it's a lot of work to reassemble, not for a PC, but for a router. First, you need to store all the things that are on the fly, which a router hates to do. The goal of a router is to get rid of the packet as quickly as possible. Second, you need to keep state information. You need to know whether this is the last, and what happens if one fragment is lost, right? If number 3 is lost, what will happen? Well, it will fail. You're unable to reassemble, so packet is lost. But if you're the router doing that, you need to wait, right? How will you detect it's lost? Well, you will wait long enough. You don't declare it's lost after 3 milliseconds. Probably after 20 seconds you declare, but that means managing timers, having things that may be stuck in your buffer for seconds, which for a router is a very, very long time. Right? So we don't want to do that in routers, and this is therefore never done. So reassembly is only at destination, and fragmentation is performed whenever the IP datagram is too large. All fragments are self-contained IP packets. That's one of the things that are important to remember. Now this is for IPv4. At IPv6, with IPv6, in principle, we don't fragment except at the source. So routers never fragment. They do what you propose, right? Which is some IPv4 routers might also refuse to fragment. Question?
Why would I fragment at the source? I would just make...
Good question. Why would I fragment at the source? Well, in principle, try not to fragment at the source. And certainly if you use TCP, it's a very bad idea to fragment at the source. Okay? But with UDP, it might be useful. Because remember, UDP is message oriented. So if you use, in your application code, you use UDP, you send one message of, let's say, 1506 bytes, then it's convenient for you to be able to send it at the source with one UDP call, and at destination to receive one block of data. So for UDP applications, it's a convenience to be able, in one socket call, to send one datagram. Now, if it's too large for the MTU, then this machine will fragment it into smaller pieces. The destination will reassemble before delivering it to the application. If any of the pieces is missing, the entire datagram is declared lost. If you don't like that, you make a UDP application that is careful enough to send blocks that are always smaller than the maximum worst thing that can happen. In practice, 1200 bytes, for example. In IPv6, we mandate that any interface, any system must be able to have at least 1280 bytes. So if you write a UDP application and you want to be sure there is never fragmentation, you make sure that your pieces, blocks of data are not larger than that. And then it will work. Fragmentation is considered harmful. It's harmful because it gives work to the destination, but the worst thing is this one. If you lose one fragment, because it's IP layer, the reassembly machine at the other end will be unable to reassemble. Therefore, it will declare it lost. Now imagine what that could cause. Imagine a network where we lose a certain fraction of the packets, and assume TCP, a stupid version of TCP, would create packets that are very large and needs to be fragmented into 10 IP packets. Assume you lose 10% of the packets. Right? Every TCP segment has a very high probability of being lost. So what will happen? TCP will retransmit. By retransmitting, we might even escalate the problem. So the unit of retransmission should be the unit of loss, which means whatever TCP sees, which are the lost segments, should never be fragmented. So with TCP, in principle, we forbid fragmenting in all cases. We do it only for UDP as a user service if you want it. To avoid fragmentation, we do what is called pathmtu discovery, on which I will conclude, and thank you for the 2 minutes of patience. As you had proposed, routers could say, oh no, this packet is too big. In fact, this is foreseen in an IP header. You can put one of the flags, which is the don't fragment flag. If you set that flag, that means routers are not allowed to fragment, even if they would like to. So normally, when you use TCP, a well-behaved operating system will set that flag. If a router cannot forward the packet because it's too large, it will drop it. And like with TTL expired, you will send back to the source an ICMP message with message too big. And it will give the MTU that this router supports. So if you do that a number of times, you can easily discover what is the largest MTU that works. A bit like with TCP, additive increase, multiplicative decrease. You start whatever works locally. If you get no pathmtu problem, that's fine. If you get a message saying, no, this is too large, then you go down to that level. And once in a while, you may try to increase again to test if things have not improved. This is called the pathmtu discovery, which is typically done systematically with IPv6 and in most implementations of IPv4 today. Yes?
What if there is a different path that has a higher MTU? I'll make the source decrease its MTU, but...
So what if there are several paths? One has a large MTU, one has... Well, as a source, in principle, in the internet, you don't control the paths taken by your packets. So if some of the packets go on two paths, this pathmtu algorithm will force you to use the MTU of the smallest MTU of all the paths. You have no way to say, I would like to choose a path that has a large MTU. That is not supported in the internet today. Voilà, thank you very much for your patience. See you tomorrow morning.